So one way of deriving the frequency of oscillation is using the bridge balance condition, because these two amplifiers have no role, just to increase the signal strength and provide the feedback. So the bridge will determine what is the frequency of oscillation of your Wien bridge oscillator. So one method of deriving F naught is using the bridge balance condition. What is the bridge balance condition? When the bridge is perfectly balanced, the product of the impedance of the opposite arms will be equal. So impedance across AD into impedance across BC will be equal to impedance across AB into impedance across CD. So this is the bridge balance condition we have. So we have one more method of deriving also using the feedback network. So I am redrawing the circuit like this. See here, for the bridge, input to the bridge is V naught and output from the bridge is VF. It is the feedback voltage. So you can see input is given to RC series and output is taken across RC parallel. So I can redraw the diagram this way. See here, output is coming. You have to look the diagram in this way. So output is coming and it is given to RC series, and feedback voltage is taken across RC parallel. And one usual notation is wherever you have j omega, it is simplified, it is taken as S. As per Laplace transform, you will take S is equal to j omega. So wherever you have the reactance of capacitor 1 by j omega, you write it as 1 by SC. That is going to be the simplification. So we'll assume all the resistance to be same and all the capacitance to be same. Assume R1 equal to R2 equal to R and C1 equal to C2 equal to C. So this forms a perfect voltage divided by S. So the feedback voltage Vf of S will be equal to the total voltage V naught of S into across what component you are going to measure. So I am going to measure the output voltage across RC parallel. So see in the equation, Vf of F equal to V naught of S into R parallel to 1 by SC divided by that resistance plus opposite resistance. Opposite is going to be R plus 1 by SC, resistance capacitance in series. So remember, I am measuring the feedback voltage across the RC parallel component. So that will come in the numerator. So take LCM Vf of F equal to V naught of S into R by 1 plus SRC by R plus 1 by SC plus R by 1 plus SRC. So take LCM throughout and expand all the terms. So you get Vf of S equal to V naught of S into SRC divided by S square, R square, C square plus 3 SRC plus 1. So this is the expression for Vf of S in terms of V naught of S. You know beta equal to ratio Vf of S by V naught of S. So divide both sides by V naught of S. You will get beta equal to S into RC divided by S square R square C square plus 3 SRC plus 1. So we know A beta equal to 1, which is the condition for oscillation. So if beta is this term, A will be 1 by beta. So it is the reciprocal of that. So S square R square C square plus 3 SRC plus 1. So once you know this, you know how to find the frequency of oscillation. So replace S by j omega and you can equate the imaginary term to 0. So if you equate the imaginary term to 0, you will get omega naught equal to 1 by RC or F naught equal to 1 by 2 pi RC. So F naught is going to be the frequency of oscillation of your Wien bridge oscillator. So at the frequency of oscillation, you will get the gain value as 3. So if we are going to use a Wien bridge oscillator using BJT, the minimum gain of the circuit should be at 3. So if you design the amplifier for gain less than 3, then you will not get sustained oscillations coming out of your Wien bridge oscillator. So this is a very, very simple oscillator, RC oscillators. The first one, what we have seen, RC phase shift oscillator, little bit complex one because we had lot of resistors and capacitor connections. But this one is very simple because you have all the components surrounding a bridge. And two common emitter amplifiers I am going to have just to amplify the signal and provide proper feedback towards